Hello, folks. It's George Leoniak, and welcome to New Geometry. Today, I am excited to be sharing some information about the crystal spiral. It's been quite a while since I've done a video on this material, but it's November, and today, November 9th or the 8th, was supposed to be a very special event in the crystal spiral about the time wave separation from the Fibonacci sequence. So I have some interesting discoveries related to this material that I'm excited to get into. And for those who are watching this, I just want you to have an open mind for the material. It might be going in one direction, but may circle back around to something else. So just keep open during the presentation here, and let's enjoy this spiral journey together. So let's see here. Here we are in the November 2023. And back when I was doing a lot of the crystal spiral videos, right around that time, this fellow from Waking Earth put out a video. I guess it has 124K views at this point about time wave spirals and their coming separation of the time wave spiral. Today, I happened to go just check and see. I guess he did his first video on this topic since then, just recently. So you may want to check that out afterwards. I am going to have a very different approach to what is shared in his video. I am a hardcore geometer, and I'm going to explore the crystal spiral from a very geometric perspective. He'll provide a lot of other information around some timelines and histories and things like that related to this that you may seriously be interested into checking out. But my approach is going to be quite different. Of course, if you watch my channel, I'm not really into the Metatronic Death Star harness language. It doesn't work for me at all. Not to say that I'm a Metatronic passionate supporter of that either. I'm certainly shown in my videos Metatron's cube has its inaccuracies. So I'm a middle of the road geometer, which really likes to look at the truth of these things. And that is what we're going to do with the crystal spiral today. So let's go ahead and take a look at the crystal spiral in this modified Cathar grid layout, which is essentially the counter-rotated squares within squares within squares, and the spiral itself will then follow along the descending square edges, just picking up the next inner one as it goes towards, which we'll talk about, a so-called center in the middle. So this past 2 weeks, this really came back because ever since I heard about this time wave separation and it came out around my videos back around 2 years ago, I was like, great, 2023, it's 2021. It's not too long to wait to find out what's going to happen with this spiral. But I listened to the fellow's video that I just showed a little bit, and he's like, well, the date moves around and things like that, so who knows when it is. But it's supposedly something supposed to happen here in November. But back to this. So here are some things that I want to discuss around the crystal spiral, and I am trying to wrap my head around a few issues, just the geometry of it, in describing this as a spiral that is often called a 1-to-2 ratio as it progresses around. Now, they say that the spiral doubles by 2 every 90-degree turn. But this whole sequence of the spiral as it moves is 135-degree angles. So I'm just arbitrarily choosing this edge length here as 1, and that would be, this is the square root of 2, because that's the same length as the cross of that square, right? The diagonal on the face of that square there. Well, that's root 2. So that whole progression to the next smaller one, this would be 0.707. This would be root 2 progression. So it's a 1 to root 2 progression, and it will double on the 90-degree angles. But what's going on with the 135? I think it is just more or less following a sequence that follows these square edges, which they call the Cathara units, which are counter-rotating around to get there. But I want to know really where the doubling sequence is in a progressive way. This chart here is not going from 1 to square root of 2 to 2 to the next number, which would be just 2 times the square root of 2, and continuing on like that. It's not doing that. So what is up with the progression that is being displayed here? So it's not really a 1 to 2 ratio. It's 1 to the square root of 2. Now, there is a spiral out there that is based on 1 to the square root of 2 spiral, and it's called the root 2 spiral. And the geometry of the root 2 spiral, this is that spiral right here, and the edge lengths, if you go this way, or if you trace around on the inside of the spiral, basically going across the inner portions of it, you would also come up with root 2, and that would be the root 2 spiral, which this is, being a 1 to root 2, but it's not the same outline as this root 2 spiral. So this is a root 2 rectangle, meaning this edge is 1 and the long edge is root 2. And that is actually found in a form, a geometric form, called the rhombic dodecahedron. Now, in my earlier videos on this subject, as I was trying to find a geometric structure that actually was the Cathara grid, trying to understand, is there a geometry to this, or is this just a flat drawing on a page of squares within squares that they drew a spiral and Cathara grid units in? So I was like, geez, if this is three-dimensional, the rhombic tricontahedron is a good fit for it, because it would look like it from one of the perspectives. But the cool thing about this is actually, from this view, this is the rhombic tricontahedron, the diamond view of it. So there's the rhombic face. This spiral here that I'm showing actually is part of the edge length of the outside edge of the form, and it would contain a root 2 spiral, which would go geometrically down to the center, proportionally following that ratio all the way towards a central spot at infinity. And that is all nested within the rhombic dodecahedron, and it's not the crystal spiral, because if I rotate this root 2 spiral to face this orientation, now it's facing us, I've just rotated the form from this to from this with the diamond, now facing us straight on. That is the same outlined orthographic projection. Well, that means that that root 2 spiral has to adjust, because it's part of the internal structure of the form, and that would give us something of a spiral that looks like this, because it's following those outer points. And once again, it is definitely not this crystal spiral. So I'm not sure about the geometric structure that the crystal spiral is. Maybe still cubes and octahedrons, like I had once thought in the previous videos. But with the discovery of this root 2 spiral, I feel that this is such a better fit for an actual 1 to root 2 spiral, because it's actually part of the edge lengths and internal structure of the form. And it is a total fractal geometry, meaning we'll have one from every edge length of this going towards the center, as well as producing smaller and smaller rhombic dodecahedra all the way down, smaller and smaller, or larger and larger, to infinity. And it is a full structure, which can be built, and this has rhombic dodecahedra, smaller ones. This is a total matrices of real crystalline type structure within this Zoom tool model here. And here is a drawing kind of isolating where one of the large rhombic dodecahedron are in this structure. as well as many small ones within there. So that's one thing I wanted to discuss around the crystal spiral is, once again, how does it fit into geometry? And I'm not sure the rhombic dodecahedron is a good fit. But with that aside, the rest of this is going to now really focus on comparing the Fibonacci spiral and the golden spiral. And the first part of this that I want to discuss is, does the crystal spiral really have a center? This is one of the big claims of the crystal spiral, and why many people like it is that it is said to start at zero at an origin spot. And if this squares within squares, if I looks like from this distance, there's a little black dot in the middle. But if I were to zoom into the same picture here, you'll see that, well, those squares just keep going. And if we could zoom in forever, we'll just continue to produce more smaller squares. So where is the start of this progression, other than if you draw it by hand? At some point, you'll not be able to draw smaller squares, so you could just say it ends there. But the diagram itself, I believe, has a flaw to it in that it does not have a central point. Now, I'm not totally one-sided saying, hey, the Fibonacci spiral here is like the replacement for this. I'm not really looking at it from that example. It's not a either or scenario. Let's just talk about the geometry of these things, okay? So Fibonacci spiral has some issues in locating a center. And when I draw out the 1, 1, 2, 3, 5, 8 progression, and this is now zoomed into this little spot here, I didn't write in the rest of the numbers, but you'll go to 13, 21, 34, 55, 89, and 144, and so on, as you continue around in that type of sequence, which is not a doubling sequence. It is the two previous numbers adding up to the next, so the 3 and the 2 will be 5 for the next segment length. Now, I'll zoom in on this in a moment, but these lines in here you're going to see are going to get a little jumbled. But the golden spiral here does have a geometric center in it, and these blue lines will go through the zoomed in portion, and there is a geometric point of origin of the spiral at a point of infinity, which does mean if we continue to zoom in and in and in, we will continue to create more and more smaller golden rectangles to a process of infinity. But there is a crosshairs of a geometric center here, location at the center of the diagram. Now, let's go ahead and take a look at the Fibonacci spiral center. Well, you see, it's a moving target. It does not have a distinct absolute center because of how it's constructed, being based on this 1 and 1, 2, 3. Well, in the beginning, if I do the, and this is the way to find the center of these spirals, is to go across the large rectangle and then the smaller rectangle, and that will give you the geometric center of the spiral origin. Now, because it's trying to slowly work its way towards golden proportion as it gets ever so large, well, that means ever so slightly, those rectangles are not always following a perfect 1 to 5 progression. So when I crisscrossed my lines through many of the Fibonacci spiral rectangle corners, they look like solid lines from this distance, or a solid line from this distance, all adding up to one solid line. But when you zoom in, you'll see that the spiral center is moving all over the place, and we'll get closer and closer to converging at a similar location, but it will never be an absolute center because it never converges at an absolute number, because phi in following the Fibonacci sequence is always going to be slightly above or slightly below when you divide the two numbers. Type in your calculator 144 divided by 89, but then type in the 256 divided by, well, what's the next one? 256. What's the other next number in the sequence? Well, whatever it is. The next number in the sequence, the 144 and the 89, then you'll get closer to phi on that one. So that's just the way the progression works. As you continue to add the previous numbers and divide the lower one to the higher one, it will continue to converge on the golden ratio of 1.618. Now, let's just take a look at this, trying to discover where the center is and why the crystal spiral one is really not any different than any of these other geometric progressions here. So we are looking at the crystal spiral here as it works its way around. Well, that is really no different than if I just put counter-rotating triangles or pentagons or hexagons, heptagons, octagons, or nonagons. If I go around, I could just continue to connect the edges of the next smaller pentagon within here all the way around to produce a spiral. So you can make spirals out of any polygon like this by just going to the next smaller polygon edge. But they all have one thing in common, and that is they don't all have a center, because if you continue to zoom into these drawings, you can continue to put smaller and smaller polygons within them, just rotating them around to continue the sequence forever. So with the infinite ability to zoom in, you can just keep adding more and more numbers. And the number of the edges just really don't matter to the sequence. So then what makes this one being more special than any of the others? Well, let's just take a little look at how to find a center in these rectangles. So we've got the root 2 rectangle here, and we have the blue and the red crossing lines, the blue and the red crossing lines, the blue and the red crossing lines. That's 1 to root 3, and that is 1 to phi rectangle for the golden spiral. So all of these and how they work out are all going to have a geometric center that is going to be presented by those 4 lines of symmetry crossing, and they are at 90-degree angles. We're going to come, or 45-degree angles between each of them. We'll come back and take a look at them. Well, let me hold on that. They may or not be at 45-degree angles. They're at 90 to each other. The red is to 90 and the blue is to 90. But they're all going to meet at the crosshairs. That will show the center of the spiral. So basically, a summary up to this point is the Fibonacci spiral, that center keeps moving around. It's an ever-moving target. And the crystal spiral, that is just counter-rotated squares, just following edge, which means you could continue to add smaller and smaller squares to it. But let's just take a divergence for just a second here, because I want to talk about the 1 to root 3 spiral. This is a very cool spiral here, 1 to root 3 rectangle. So if you put these root 3 rectangles together in this drawing here, you'll see that it creates the vesica Pisces, and you have many, many smaller vesicas that can be drawn in. But when we crisscross all the rectangles, you're going to get 2 equilateral triangles nestled within inside one another, just like this drawing, and that will go down to the infinity spot within the root 3 spiral at the center of this drawing that all of them share. Now, this drawing on the right here is the same as the one on the left, and this is what Gianvallo calls one of his most important drawings he ever did. It's the spirals of light drawing based on the root 3 spiral. But what is also based on the drawing is this on the next page. In Gianvallo's book, he basically says later in his book, in the last 2 chapters, he basically says this sequence of circle pattern here that I used to draw this image, well, that comes from the same drawing that he said was Lucifer's creation, which is a distortion of the flower of life, because the geometric center is not on the center of the flower of life design. So I don't know, that's just a really mixed up story to me, because his most important drawing of the Vesica Pisces, putting the spirals of light on the center of a vesica basically means that, because it's off center here, is basically saying that it's Lucifer's creation, which I don't know. Things really got mixed up in geometry, but he didn't like this outline of the circles here, how they come out, because you start with a seed of life, and that should be the one geometric center. But if you continue to draw smaller and smaller vesicas inside, you're going to target location is going to be the center of vesica, which is to draw this. This is your circle template to use. You don't have to draw all the circles, but it can be done just like this. But that is the origin of the start of what he called a double rotation in Lucifer's creation. You know, another trying to outwar type of scenario here in the geometry, similar to how Cathara is saying the Metatronics have a problem, but Metatronics have an issue. They all got issues. Things are really mixed up. I like to talk about the geometry. It really simplifies things. To look at really what's happening here is that it's just another way to draw this, and it's not 2 eyes staring you down like that, like he says in the book. So, but you can draw this spirals of light, which is cool, like 2 equilateral triangles, and it's basically just following around equilateral triangles as you work your way around to create smaller and smaller. So anyway, that was just one little aside here that I wanted to cover with the root 3 spiral, because it is a cool spiral and it is neat how it shows up this way, but that is not really what this discussion is about. We're going to get back to the crystal spiral here in just a moment. So I'm not really on any side here beside geometry side and sacred geometry side, but there are a lot of inconsistencies, as I just pointed out, in our books that convey this information of this. First, this is a good one, the spiral of light and Lucifer's creation, 2 drawings from the same book. They're the one and the same thing. It's confusing, right? So anyway, let's go on a little bit further here, because what I really wanted to find out now with the crystal spiral in my journey with trying to understand more about this geometry was, how do we find the center of different polygons? So for instance, here is the hexagon and here is the root 3 spiral, and I can add the red and the blue lines to come up with a geometric center here. And I was like, oh, well, there's a regular triangle. And that what that wants to do is it also wants to create a root 3, because it's really just half. But I was like, I could do some very cool things here with a pentagon and make a golden spiral basically inside a pentagon, but it's not a traditional rectangle with 90-degree edges and 90-degree angles between the corners. And I could even do a heptagon one by doing the same thing, by just following similar rules throughout each of them, But I'm also locating, by doing that, the key spot within each of these where the center is. But when I got to the square, that was really interesting because I was like, well, what do I do about the square? Because all these other ones are going to have the center located off center of the polygon. And that helped give me some insight into maybe why the crystal spiral is saying that the origin is at the center and it's using the square as the outer polygon. So we have the red and the blue crystal. There's really no other way to draw this in to try and find the location of the center point. It's got to be the center of that polygon. But let's just take a quick look at this as a little bit more of a close-up with the nonagon. And here we could just draw 4 lines going across a nonagon. And we got this tilted nonagon. So this is like a nonagon spiral. Here's the spiral route that it would follow in yellow, following those 90-degree turns. And that is just the key thing. All the spirals I'm going to show you are going to have a 90-degree turn as it works through, in this case, these rhombuses. And these edges are proportioned. So it has a proportion as it continues to go around the edges to create a spiral that's going to converge where the red and blue lines crisscross out the center. So every spiral I'm showing you has got this 90-degree turn within it. And then it made me wonder, well, why is the crystal spiral going to be the exception to that rule? Right? So like back at slide number 2 here, why do we have to have this 135-degree angle? It seems too simplistic, and there's nothing the matter with simplistic geometry to capture the most profound insights in geometry, for sure. But it seems more like, well, let's just follow the square edges, but maybe it's missing something with trying to connect everything and say this is a doubling sequence when it's really not, when it's a 1 to 2, because it's got a 135-degree angle in there. It's not a 90-degree angle. We really want to find something that has segments that are doubling to follow a spiral, so that the spiral is actually doubling, not like every 90-degree turn, but every other segment it does that. I don't get it. There's two doubling sequences in here then, not just one, and that's confusing. So that diagram doesn't really capture the sentiment of a doubling sequence. So I went back to the drawing board with the square. Basically, after that was, well, if this has got a geometric center compared to all these other polygons, which are always going to have an off center, right? When I do these different constructions, they're going to be off-centered there. So let's revisit the square. So I just drew out the squares and I was like, well, the only thing I could really do here is that, yes, I can start to put in other squares, and I did other squares just like the Cathar grid. But I wasn't sold on the idea of just working my way around, because I already know that that is never going to really bring me to the 0 point at the center of this diagram. So there must be some other way to find a route to the center there that is going to be following a progression that is going to be a doubling sequence without the 135-degree angle and the 1 to root 2 progression. Okay, we want basically 1 to 1, 1 to 2, 2 to 4, 4 to 8 progression following a 90-degree. And within this diagram, I'm able to, and you don't need the grid work in here, but I'll show you, we're going to come back to that a little bit later. You can just draw your squares, counter-rotated at 45-degree angles. And if I go ahead and just connect from the corner of one square to the corner, down to the corner, down to the corner, and so on and so forth, well, we come up with something that starts with a 1, 2, 4, 8, 16, 32, 64. And these little dotted segments here, they're not a dotted line. Those are actually the increments of 1 at the beginning over here, okay? And I'm going to get to the 0 and 1 and where 1 and 1 and 0 are in this in a little bit. But this is just outlining my progression of learning about this spiral, because this is a true ratio spiral of 1 to 2, because we're going to double it, right? 2, 4, 8, 16, 32, 64. And like I said, these dotted lines are the actual increments of 1 down here. So there are actually 32 little segments here that I counted out, and 64 little segments, 68, 8 little segments starting with 1, which means you could trace this line all the way back to the beginning and add it all up and show the sort of geometric progression that the actual sequence that they're trying to show here is based on. Oh, this is where I had the 256 number in my head before. 0 and 1, 0, 1, 1, 0, see, it adds up to 2, but you could always go back to 0. So that was the thing they're trying to illustrate there in that diagram, which this doesn't show as a diagram, because you have root 2, 1, square root of 0.5, and 0.5, right? So I don't know, it didn't make sense to me. But this makes perfect sense, and it's nicely in the same diagram because we have the squares, but it's not the crystal spiral, but it is actually showing the doubling sequence. Now, how I came up with that idea was actually because I knew about this square, following the square, to produce that in the golden ratio spiral. And that will start with, let's say, 1 here, 5, 5 squared, 5 third, 5 to the 4th, 5th, and 6th, as we go around, and it follows from corner to square, corner to square, corner to square, and we could turn that into a nice curved golden spiral. And I knew that that spiral is infinitely going to the center as it works its way to the center. And this one will do the same thing. But here's the thing. It is also now set up to infinitely go to the center. So we're going to revisit that, and how there is a bit of an issue with, well, where's 0 and 1 getting into this? And I'll get to that in a minute, of how we can figure out the geometry to convey that in a way that will illustrate the 0, 1, plus 1, 2, 4 progression, right? The doubling sequence. But this is a doubling sequence spiral, and it is going to converge at also a point of infinity at the center, and also the golden rectangle and spiral. So these are the rectangle outlines, and yep, the rectangles are going to be tilted in this, but they don't have to be. This one we could draw right here, and this one is a little trickier methods to figure out how to draw this one, because this spiral, we're going to convert it in a little bit so that it will be flat, but that's going to change the dynamic of our square grid that we're using. Okay, so one thing about the spiral that you'll see here before I jump to that next slide is the golden rectangle is square, 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 all the way down. Of course, these are larger golden rectangles. But when I come over here to the doubling sequence spiral, the 1 to 2, what we do is basically the spiral is, let's go to the larger one. Well, I need to show you the rectangle. So this rectangle is the same as this one. So let's hop over to this page. Well, let's take a look at this one. Okay, so here's the rectangle, and it is 1 square, 1 square, and 2 squares. So there is a portion. This is basically into quarters. 1, 2, 1, 2, 3, 4. It's divided into 4, and basically this is this square, the next one is going to go through, is 1/4, and then here's a larger square, right? And then we have 2 squares, and then we come over to this one. Now we're going to have that one single square, and we're going to divide that into 2. So we're going to have basically 2 to 1, right? So here's one large square, and here are the two little squares. Here's one large square. There's the two little squares that it came from, one large square, and the two little squares that it came from. So the sequence there is basically built on these squares, but we're going to get this little leftover blank spot that has no spiral in it. And I was wondering about that, but then I realized, well, that is really no different than how the silver spiral operates, or any of the metallic mean spirals, which the bronze spiral, silver spiral, golden spiral. The golden spiral is the only one, like I'm showing here, that doesn't have that little remainder left over. It is just squares that you could follow that rectangle around and produce a spiral. But the silver spiral, as you could see here, it has a whole other square over here that's just hanging out as the spiral goes over here. But to find the center of the spiral, we use the whole blue line, right, from across the whole face. This is a 1 to 2.414 ratio. So this segment would be 2.414. This would be 1. Okay, similarly with the edges, right? That ratio is going to maintain itself, but we use the whole blue line across the whole thing. And that will do the same thing here for the doubling sequence spiral. We're going to go ahead and send our blue line through that one and that one. And now our remainder, instead of it being a whole square over there, is going to be this little proportion left over here. And remember, it is going to be just two squares. Divide that square in half. Then we have two squares, divide that square in half, two squares, divide that square in half. That's the 1 to 2 ratio doubling sequence between those two squares. And that's how the spiral is produced and how we get the center of it by drawing it like that. Okay, but as I'm saying, there's a little bit of an issue there, but maybe there is no absolute zero. We like to think so, but if we want a zero, we have to let go of this type of diagram that is going to have kind of infinite center of the squares kind of going in the center like this. And we can start at 0, right dead center in the diagram. But what happens is we have to, as we go to follow our doubling sequence, the lines are not going to be so easy to pick up. There's no point at all anymore, besides just the initial starting counter-rotated squares to get this going. There's no point to add in the rest of the Cathar grid squares like this, because what's going to happen in this diagram is that they're going to go by and they're going to like land way out here and they're going to land here. Well, that's going to be part of a circle, but it's not obviously going to show up in a good way that's easy. And I couldn't find an easy way just to extend this circle template out to pick up these points. So at that point, we just kind of, we could extend lines, we could do other things to it. And pretty much I found, I'll show you what the solution is to draw this in just a second. But for what I discovered so far here, let's just say we got 0 in the middle. Great, we've established that. So our first line out from there on this is going to be 1. And then our first turn is going to be 1. Well, that's 2. Great. Okay, there we go. We got 0 and 1. Bam. 0 and 1. Here's the second one. We got 0, 1, 1, 2. So we got 2. We got the next one's going to be 4. We're going to double that. We're going to have 1, 1, 2. Oh, 4. Okay, now we're going to go 0, 1, 2, 4. 0, 1, 1, 2, 4. That gives us 8. This is going to show precisely what the Cathar grid, or what the crystal spiral is wanting to demonstrate, but is getting caught up with the root 2 135-degree angle. So it doesn't make sense. It's not a doubling sequence. The way they're framing it as a doubling sequence, but it's not actually showing you this. You have to skip numbers. If you skip values and say, well, every 90-degree turn, once you get past the 135-degree turn, well, then it does that. But this is going to just follow this out. I mean, like, add it all up. 0, 1, 1, 2, 4, 8, 16, 32. Okay, well, that's right here. 0, 1, 1, 2, 4, 8, 16, 32. It's just not so simple. It's not simply in that diagram that is just these counter-rotated squares. We could draw it like this, but like I said, this will put you into the golden ratio infinity camp, which is like this is going to continue to go around and around. I don't know. We can never really connect it back to being one. We're going to have squares going around. We'll follow it around like that, but we won't be able to get to the point of infinity there. But it has a geometric center, at least for that diagram. Okay, but here is the solution to drawing it, basically, is, well, we don't need circles at all. We just need graph paper. So just get some graph paper, make a big square on it, and that'll define the boundaries of it, and locate the center point, crisscross the blue and red lines. There's our X marks a spot. There's 0, and then we just go a diagonal of a square out to 1, go another diagonal 1, then go 2 diagonal, go 4, go 8, go 16, go 32. If you got big graph paper, keep going. And that's the easiest solution to create the 1 to 2 spiral, because if you try to do it all with like the circles like I'm doing here, you're only going to get so far before you're going to realize, well, I just have to keep extending lines to pick up farther points. But if I want to illustrate a doubling sequence, then just use graph paper. And then I was like, oh, well, I could draw the Fibonacci spiral on graph paper. So we're going to revisit that, and we're going to compare these two spirals. Okay, so we're doing a totally different thing with the Krystal spiral at this point, because basically I think, like, I know that there's a lot of other philosophy built around the Cathar grid, and the spiral is a part of that whole megalopolis of philosophy that's associated with it. But look at it from a geometric standpoint, I just don't see how that spiral is illustrating one of their fundamental tenets of the doubling sequence, unless you're good with doubling both 1 and root 2 each time. But if you want to illustrate it easily, then, and follow kind of the rules of every other spiral that has a, that's shown as a 90-degree turn rather than a 135-degree turn, essentially it's not any different, like I illustrated before, than any other one of these spirals. And we could just start any group with the whatever this is, we call it the quasi-crystal spiral because it's the forbidden symmetry of 5. We could call any of these other spirals. Here's the hexagon. There's the Metatronic spiral. All right, this is the crystal. This is the quasi-crystal. This is the Metatronic spiral. We don't have a heptagon group yet, but we might as well. That's what I mean. That's what it's like. Okay, so maybe there's good stuff in the rest of the philosophy that's all good and interesting, but it's not true to its doubling sequence formula of how the spiral operates in finding the center. It doesn't have a center. This at least has a center, and it follows the progression. And it's not some opposition Metatronic agenda. It's just what it is, It's just like, this is how this spiral works, 1 to 2 ratio. Okay, so I went back to the Krystal spiral and was like, okay, well, let's see. Well, maybe the Krystal spiral has this kind of like embedded in it, and it sort of does. But I put the rectangle around here, and because if I go to this edge and I extend this line over here, I could create my 1 to 2 dotted lines, and that's going to kind of reconnect back up with this little red segment. But what happens is the spiral is going to take a turn well away from the center, because the center now is going to want to end up over here, because it's following a 1 to 2 progression when you remove this 135-degree angle. It's only going to appear to go to the center, because it's not even center. It's only going to appear to go to the center when we follow this 135-degree angle around here. But if we start to actually follow the doubling sequence 90-degree turn, then all of a sudden our center is going to be way over here. But at least it's going to be a center, and centers everywhere. So like I said here, we're good, right? doesn't matter. The center's here, that's fine. Because the center's everywhere anyway. So it's a little bit of a silly notion to keep trying to find where the center is, but I could understand a little bit of why it may have some importance in comparison these spirals. But what we want to do, if you really want this at the center, is shift that back over to here. So like I said, you don't need to use like sacred geometry, just go to Staples and buy graph paper and you're good to go. But if you want to explore sacred geometry more and you don't want to just keep doing graph paper and using the Fibonacci sequence or this spiral, and you want to use sacred geometry, then I would say do the golden spiral, because that's going to really open you up to drawing and understanding sacred proportions of all these different roots, all these different spirals here, by needing to draw sacred geometry to get these. So this is why I had to draw these diagrams to draw this, whereas even the crystal spiral, even this one here, you don't need circles to do this. You could just, once again, you could just do this in graph paper. So these all need, as I was saying over here in this slide, they all need some understanding of how ratios and proportions work to actually develop these. And the golden spiral is led to my discoveries of how to find the center of all these other different types of spirals. So when you're interested in wanting to explore sacred geometry and really getting into understanding sacred ratio and proportion beyond the 1-to-2 relationship, then you need other circles and other ways of mastering the compass. Like I have mastering of the compass way of sacred geometry course to start to master the proportions in the sacred geometry, so that we're basically out of the grid. All right. But this is cool. I really like this spiral. The doubling sequence spiral is awesome. It's, once again, it's tricky to capture it at 0 with just using the compass and straight edge techniques. All right, so let's take a look at, let's now go back to the Timewave material, because I've done enough to describe a big change in how I pictured the doubling sequence spiral. And I want to bring that back into this Timewave discussion without looking at the crystal spiral version of it, because it really is like comparing apples and oranges. It doesn't work when you have one spiral that is built on this 135-degree angle, which we know the crystal spiral is going around, and all these other spirals are all built on the 90-degree turn. So we're not even comparing the same thing in the discussion. And a crystal spiral is really the only one that does that. So if we're going to compare the crystal spiral, what we should be comparing it to is not all these other things that are following this 90-degree turn. We should be comparing it to these spirals, okay? Because these are all the spirals that follow those types of rules. So compare it to this and not something that is following the 90-degree turn. Now, that doesn't mean that the Fibonacci spiral, as I stated, doesn't have issues with finding a center and all those other things. There may still be some very good valid points to what the crystal spiral is describing and talking about, but I want to now, in my working of a 1-to-2 ratio spiral that I feel is playing by the rules of the 90-degree turn of all the other spirals, let's see what happens now with our Timewave discussion when we work our way around. Okay, so when I did this diagram, and this one is based on the squares in the center method, because it really doesn't matter. It's going to give us the implied understanding that there's a 0 in the middle. Let's just call it infinity at this point. But as I was working my way around, because my original drawings, I started the spiral at this corner point, and then they diverge. But if I go out from that point and I added a few additional layers on of squares here to continue the spiral progression, here is the actual true golden spiral that we're comparing to. This is not the Fibonacci spiral. And this is the doubling sequence spiral, the 1 to 2, as they meet at this point and then they separate again. And that's really what is this time wave separation. I don't know if there's any date or anything that's going to like be super specific about when that what's going to happen, or whether the spirals are just going to do this anyway. Who knows? But this is what came to me in the last couple weeks and these drawings of last night. So I'll share this bit of information because I felt it was important to kind of try and bring this back to the first slide of the discussion, and really what a lot of hubbub around the crystal spiral and a lot of attention being brought to it is around this time wave separation. But let's compare spirals that are now following the 90-degree turn. Really nothing different is going to happen in terms of, I mean, you're dealing with the different look of the spiral. That's one thing. So we're not looking at crystal spiral. I mean, we're looking at a 1 to 2 ratio spiral. But of course, as we go around from the center, we're going to work our way around, and we are going to have the red spiral is our Fibonacci spiral, and our blue spiral is our 1 to 2 spiral. And as you can see, I don't have all the numbers in the inside, but I got 256, 512. So this is the doubling, right? And then these numbers are the Fibonacci sequence, adding the 2 lower to get the next higher, adding the 2 lower to get to the next higher. So I'm working my way around there, and the 2 spirals are following each other. And I'll show you what's happening in the interior in just a moment. So I'm working my way around, and the red spiral is on the outside. And as we come to this point right here, the blue spiral is going to cross the red spiral. And at that point, I don't believe they'll cross again, because the red is just going to stay interior to the blue, and the blue is really doubling fast. So they're going to continue to take that 90-degree turn, but the blue spiral is just going to far exceed the red spiral because it's increasing at a much faster rate. And that happens here. It's very cool in this diagram because I could precisely pinpoint that location, because it's 32 little units, which are from way down in here, because I start at 1, right? So 1 is way down in the middle, 0 to 1. And these little units from 1024 to the remainder, well, it's 919 to this point, because I could count out little individual units, which I did, 105 of them all the way up to here, 32 from here to here. That's the precise meeting point where those 2 cross. Now, if you're actually not dealing with these 90-degree turns and you are drawing the spirals, the spiral crossing location is going to be at a different point, but this at least can help me show how the interaction is actually happening at a specific point in time here, or in on the page right here at 919. The length 919 of 1024 right there. And let's go ahead and take a little bit of a look at the interior of the diagram. So at this point, I have added in the golden spiral. So I've taken out the rectangles and I've added the golden spiral. I've made that the gold one. And I've added in the red spiral once again. That's the Fibonacci one, and the blue spiral. Here's that same little intersection point, 919. And the golden spiral for right now is on the outside of all of them. But the next turn below, the blue will cross the golden one down here. So that same thing's going to happen because, like I said, the blue spiral, the 1 to 2 one is the doubling spiral, where the Fibonacci and golden spiral are moving in a golden ratio progression, and the Fibonacci spiral is adding the 2 previous ones to get the new one. That's just not doubling, right? So the blue spiral is going to cross those at some point. Now, I've added in a couple other things, these long lines here, okay? Now, that is going to give us two things. It's going to give us the center of the golden spiral. And now we're going to zoom in to the center point on this diagram of what we were just looking at, but now I'm down into the center of the drawing, and I have the same golden spiral. I have the blue spiral, which is only a little piece of it, and it's purple here. I'll explain that in a sec. And I've got the red spiral. Okay, that's the Fibonacci. Now, what's going on here is the 0 point of the starting point is where it's purple, 0 to 1. Here's 2, the 1 again. Here's the 2 length. There's the 3 and the 4. Okay, because what I did here is I said, well, let's start the Fibonacci spiral, because now I'm on graph paper. I'm thinking in terms of graph paper here. So I could start 1 and 1, right? So I could go 1 and 1, and then 2, and then I'm up to 3. Oh, now this spiral takes a turn. The red one does, and 4 keeps going because that's the doubling sequence. It's only a 1 unit difference. All right, no problems. And remember, the golden spiral, that is where this large golden crosshair is, and that's centered right on the same spot. So that's your 0 point, point of infinity. Golden spiral's on there. It's going to keep working its way around. It's not just going to go 0 and on. It's going to go keep going around. I just had to stop the line because at some point I can't draw infinitely going in there, but that's what's going on. Now, we're going to revisit what happened with the Fibonacci spiral, because remember, the Fibonacci spiral, I am starting 1 and 1, and we know that that's not a spiral for that at all at that point, because it's going to try and mimic the golden ratio, but 1 to 1 is not close to the golden ratio, right? And then we're going to go to 2, and then we're going to go to 3. You know, still not golden ratio when we divide 3 and 2, right? You got to go far out in the diagram, right? Remember, you got to go way out here, right, to that outer rectangle to draw the line at the center. So that's what I did. So I'm taking that line for the Fibonacci to go from way out on the corners of like one of those distal rectangles, way out there. And then I'm sending the line to the center, and I'm thinking, because from a distance, from far away, you can't tell. It looks like it's going through the center, right? And in fact, here's my little bit of golden line, and there's the other line that is one of the rectangles. It's just a slightly different color that is just ever so slightly off that golden line. It's a thin black line. And you can see where it picks up right there at that dot. That's a crossing point, and that's the anchoring point that I'm drawing that from. And as we do that, what happens is, oh, it's off center. It's not going back through 0, right? It's 2 centers now all of a sudden, because I have the golden spiral of where it should be if it's going to mimic the golden spiral. But like I said, it's going to be a moving target from where 0 is. So at least this geometric drawing of this is going to show that the Fibonacci spiral, even if you start your first, I mean, it's kind of common sense. If you start 1 to 1, 2, 3, and go 5 and all the way out to 8 and 13, well, that when I draw those long lines, it's not going to come back to where you started. It will not come back as far as you go. It will never come back to the starting point when you try to locate where the center of your diagram is. So all those diagrams that you may see on the internet of Fibonacci spirals out there that do this crosshair method, it's only an optical illusion. It's no more of it's the same type of optical illusion of saying, if I just keep drawing smaller squares, that eventually, that little square that disappears out of my sight, well, that must be the end point. But this is now your crosshairs on those spirals, like trying to find the center where you think are back where you started, but it's not going to be where you started. It's going to be off center. So it's just interesting for me to explore it this way, because There are some interesting things that are related to crystal spiral thought processes around this of, well, the Fibonacci spiral is going to be off center. I'm just doing it and showing it in a totally different way. And of course, the two spirals are going to cross. I mean, it's just like a given. Now, how do you locate that in time of when that crossing was going to be or where that spiral will be from a drawing like this to what's happening today on November 9th, and whether that has to be with your 135-degree angle, because their little key meeting spot in the crystal spiral is at, I think, 144 point, right, where the crystal spiral, the Fibonacci sequence comes around to 144. And at this point, I'm at 987, making my turn over here. Now, people love 144 because it adds up to 9 and harmonic of speed of light. And yeah, 144, great. That all fits good. What does not 919 mean? I'm not sure. But I'm not really looking at it that way because, like I said, I just want to compare two spirals that are essentially operating under the same conditions, which is they're 90-degree turns like that. Now, let's go back, and we're almost to the end, second to the last slide here, but we're essentially, this drawing is this drawing that I showed on the page before, but I just put the rectangles back in here. There are 3 rectangles, just a portion of it. They're small rectangles. Remember, they go way far out. But I just have the small rectangles. I have the golden rectangle, the gold one. I have the blue one, which is the 1-to-2 ratio, and the red one being the Fibonacci one. And once again, I'm just illustrating now within these small rectangles how the spirals are following the squares, right? And remember, the purple in the middle is where the Fibonacci and the 1-to-2 doubling are following now each other. Now, the golden rectangle really never follows that sequence at all. It's already outside of that right from the get-go, because remember, from 0, there's a lot of little progressions before you just go from 0 to 1. You go through a whole infinite golden ratio progression, if there ever is. There's no 0, is infinite. So whatever that is, it's where that's crosshairs is where it starts. That just goes on and on and on. But the 2 Fibonacci spiral, in my choice of doing this, I said, let's start with 2 squares. It was easy to do. And that helped me illustrate that when we draw the rectangle, now remember, this line is going way out to a large rectangle that is close to golden proportion at that point. That does not converge back at 0. It's going to be off center here. Now, metaphysically, I don't know. Like, I'm not here to try and describe that all. I'm hoping to instill some curiosity to look at these diagrams, look at what the crystal spiral drawing is for what it is, and look at this information for what it is from a geometric standpoint without loading in all the philosophy of the 12-tree Cathara grid and all that sort of stuff. And we come up with some similarities in, the spirals crossing far out. Great, okay, we knew that was going to happen. How did we predict the time of that from this diagram? I'm not sure, but we could see that the Fibonacci spiral has these 2 origins, which means that the starting of it is not where it eventually ends up. Now, but we knew that was going to happen anyway. That's not a surprise. Now, remember, it's always going to be approximation of the golden mean, and we know the golden mean spiral, which is always a perfect progression of 1-to-5 segments ratio between each segment. That's always going to be like that. So it's always going to be able to have those crosshairs meet precisely in the middle and always through these corners, always. So, all right, there's the 3 comparison of the 3 of those, and I showed the root through it, 3 and 5, root 2. I could add those in and do something similar. They're going to find the same progression. They're just going to follow a different spiral course. And, it's that's just the way this is going to happen. And of course, the doubling sequence is going to be the largest of all those. So it's going to cross all those spirals at some point. Okay, so whatever happened in the crystal spiral? Well, I hope I feel like I talked enough about it within there, but I did diverge quite a bit from this geometry and didn't use this for any of those comparisons once I got into the whole time wave part, because like I said, it didn't make sense for me as a geometer, like to study deep into geometry, something that had this 135-degree angle when I'm comparing everything else with a 90-degree angle. But like I said, I feel there are some other issues with it. Now, I know this is great against a lot of people who really love the design of the Cathara grid. I don't know where the center is unless this is also a convergence at zero type square thing. Great, I could give that to you. But the more of the issue that I think I was describing here is that I don't perceive it, and maybe I'm not understanding it fully. I do understand that if I go every other 90-degree turn, but I'm missing this whole section, which essentially turns into my 1 to 2 spiral that I'm producing here, showing you here. But you keep trimming this off, basically because it just fits into the diagram here, or the Cathara grid keeps trimming it off like this, rather than completing the actual doubling sequence and always turning it into 2 doubling sequences, which are going to be a root 2 doubling sequence. All those are going to double through root 2, and 1 to 2 to 4 doubling sequence like that for all the whole numbers. So you have 2 doubling sequence. One is a rational numbering doubling sequence, and the other is a rational doubling sequence, all in the same diagram, based on this 135-degree angle. And I don't know. Maybe that's 135-degree angle is going to be fine for the geometric progression, but there is something for all the other geometry of all the other spirals that take this 90-degree turn without adding in the extension piece here in the middle. But like I say at the bottom here, if you really love the design and what it represents to you, well, keep on spiraling on the time wave and enjoy the journey. I had a lot of fun and interest in this topic to explore it and produce all this material for you. So I thank you for sticking with me, and hopefully you kept that open mind to follow my little spiraling journey with that. And hopefully there's some interesting information there that someone else will pick up and explore. Please feel free to contact me with any questions, observations, or comments around the material. And I look forward to producing another awesome video. And I would also recommend that you check out my previous video on this, the journey through the dimensions, which is going to take you on a geometric journey through the geometric dimensions, which is going to have a lot of information about that rhombic dodecahedron and the Belinsky dodecahedron, which was based on those earlier observations of how the spirals are at the center of the actual three-dimensional geometric structures. In addition, check out the New Geometers Facebook group. Great group over there. Almost 4,000, I guess 4,000 people in that group now. So go check out that, and check out the New Geometry course site for any other additional lessons on sacred geometry and upcoming apprenticeships and everything like that. All right, everybody, much love and appreciation. Thanks for joining me. I'll talk to you next time. Bye-bye.